Hello, this is Nick of Time. Welcome to this, our 28th talk in our series on time. And we've also been talking a lot about special relativity and how it treats time. As this picture shows, it goes into some more detail about the problems of special relativity. It says space-time has no physicality, yet the universe is entirely physical. And we've talked about how if we try to interpret special relativity as describing what's happening physically, we quickly come into logical contradictions, such as A's clock is slower than B's clock, and B's clock is slower than A's clock. So basically, special relativity describes how each observer observes the world according to its relativistic model. And all of these observers seem to contradict each other in their observations of the world, yet special relativity says they're all equally valid. So that certainly implies it's not talking directly about what's physically happening. Today's talk will focus on this theme. Special relativity simulates Lorentz relativity. So we'll be talking about special relativity in more general terms. We'll be talking about time and length and kinematics. Now, if you remember, Lorentz developed a Lorentz ether theory in the late 1800s, and the top conceptual layer of Lorentz ether theory was Lorentz relativity. In Lorentz relativity, you have absolute velocity with respect to a single preferred frame, which Lorentz thought was the rest frame of the ether. And in that theory, you'd have light moving through the medium of the ether. So the ether frame was the one frame where light, the speed of light would be c in all directions, at least in a vacuum. In addition, if an object was moving with respect to that single preferred frame, the ether rest frame, it would physically contract in the direction of its motion with respect to the ether frame. Similarly, if a clock was moving with absolute velocity with respect to the ether rest frame, it would slow down, and the faster it went with respect to the ether rest frame, the slower it would accumulate proper time. So this meant there was a whole hierarchy of inertial frames, where the frames were ordered by their velocity with respect to the single preferred frame, the ether rest frame. Now, Lorentz relativity doesn't go into the details of the properties of the ether, or even that there is an ether that exists. It's just a high-level conceptual view. So, what does special relativity do with respect to Lorentz relativity? Well, it says that each inertial frame simulates the single preferred frame of Lorentz relativity. In other words, each observer, individually and separately, sees the world as though they're simulating the view from the single preferred frame in Lorentz relativity. Okay, we're going to go to the second bullet, but before we get into that, let me describe some terminology. In Einstein's original paper on special relativity in 1905, he talked about the stationary frame. But there was no absolute stationary frame in special relativity. And there was no absolute motion. So he talked about the stationary frame. What that really meant was the observer's frame, because the observer is stationary in his own frame. And that's by definition. The observer's frame is the frame that he's stationary in. And all other frames would be the moving frame, or could be a moving frame. So, in special relativity, the stationary frame simulates being the single preferred frame in Lorentz relativity. And it does that by saying that you assume that the speed of light in all directions in vacuum is c. And that's part of your physical model. Second, it's the meter stick that's at rest in the observer frame is the longest meter stick, because all other meter sticks that are moving with respect to the observer's frame are seen as contracting in the line of motion with respect to the observer's frame. And third, the observer sees his clock as being the fastest clock, as he sees all other clocks that are moving with respect to his frame as slowing down, and the faster they move with respect to his rest frame, the slower they seem to accumulate proper time. And the fourth bullet, an object's kinetic energy and momentum are seen as a function of velocity with respect to the stationary frame, the observer's frame. So it's like each observer has absolute velocity, but each observer has a different absolute velocity, namely velocity with respect to their particular rest frame. So those are, straightforward statements, and that's how special relativity simulates Lorentz relativity. Let's continue on that theme. Let's look at another aspect of this simulation. We'll look at the relativistic Doppler effect. Now, Professor Frankel, in a paper, shows that the relativistic Doppler effect is equivalent to a normal Doppler effect, where waves travel through a medium at rest. For example, the Doppler effect for sound waves moving through air, and you get the Doppler effect of an increase or decrease in the pitch of the sound depending on how the source moves with respect to the medium and how the observer or the receiver of the sound waves is moving with respect to the medium, the air in this case. If you want details, you can pause this frame and copy the reference here in the second bullet and note that the paper just covers the two-dimensional case, but I'm going to go into this in a little bit more detail. Okay, so the standard Doppler effect, where both the observer and the source are moving relative to the medium, for example, sound moving through air, the equation for the standard Doppler effect, in this case, would use both the velocity of the source with respect to the medium and the velocity of the observer with respect to the medium. So the rest frame of the medium is treated like the absolute frame, and then we have the absolute velocity of the source with respect to it, the absolute velocity of the observer with respect to it. But Frankel shows, through algebraic manipulation, that one can replace the velocity of the source and the velocity of the object, of the observer with respect to the medium, by their relative velocity and get the relativistic Doppler effect. So we have two totally different models. One is the classic physical model that's implying what the physics of the effects are, and the other, the special relativity one, replaces this cause and effect part of the model with relative velocity, where it isn't. The relative velocity is not the cause of the effect. It's the absolute velocities with respect to the medium carrying the wave. So the one further interesting point is, for this second bullet to work, to be able to replace the two absolute velocities with relative velocity between the source and the observer, one must use the relativistic law of addition of velocities. So you start at the rest frame of the medium, and then you compute velocity and relative velocity with respect to that. Okay. So what are the implications of viewing special relativity as being a simulation of Lorentz relativity? Well, first, if Lorentz relativity is correct, and one is using special relativity and happens to be in the Lorentz preferred frame, special relativity will seem correct, because the equations are the same, except Lorentz relativity uses absolute velocity and special relativity uses relative velocity. But if the observer is using special relativity and he's in the absolute frame, the preferred frame, then he might think he's using relative velocity, but he'd be actually using absolute velocity. So again, in that case, if Lorentz relativity is correct, special relativity will seem to be correct. And a whole lot of the empirical evidence that's alleged to support special relativity, it appears that that's taken in Lorentz's preferred frame. But the physicists have really sort of dismissed and forgotten about Lorentz relativity, so they're not even thinking about that. It not only would be consistent with special relativity, but also consistent with Lorentz relativity. Okay, to expand on this first bullet, we note that some physics effects and values are invariant. So if Lorentz relativity is correct, then special relativity will seem correct for those invariant effects and values in all inertial frames. And we've already discussed one of those, and that's the net proper time difference in a twin paradox. That's invariant no matter what the home frame is, the stay-at-home frame is, if you have the same relative velocity between the stay-at-home twin and the traveling twin on the way out and the way in, you're going to calculate the same proper time difference for the round trip, regardless of which frame the round trip starts from. So that value is invariant. Another example is collisions. If Lorentz relativity is correct, and one uses conservation of kinetic energy and momentum, then special relativity will seem correct regardless of what frame it's used for, because a lot of those things are invariant. A lot of the results and key values are invariant for collisions. Okay. Now, that's just a short overview of special relativity simulating Lorentz relativity. It's an interesting perspective to keep in mind and to understand and be able to properly interpret empirical data results. Now we have 3 other talks prepared, so this will give you the titles of those. I'm going to go back and talk to the twin paradox, and you might say, oh, we've covered that this way and that. But relativists, seeing there were problems with talking about the time dilation equation, invoked Minkowski space-time diagrams and gave a pictorial argument for why special relativity was correct for the twin paradox. So we'll look at that, and our rebuttal will be pictorial, so I think that will be more memorable and perhaps give you even deeper insight into the lacking of special relativity regarding the twin paradox. Second, talk about the history of the treatment of time in physics. And I haven't done too much on that. Talked a little bit about Newton. And most of that information comes from Professor Lee Smolin, so I'm indebted to him on that and his book, Time Reborn, which is an excellent book. And both he and I came to the same conclusion about the problem about the treatment of time in modern physics, namely that time has really been washed out of physics model. And Smolin has one solution, and I have a really quite different solution. So the second half of that long talk will be about that, and there'll be some overlap. I think it'll be good to get those ideas across a second time, and from a little bit different perspectives, some new points and some different perspectives. And the third will be how to win a twin paradox debate. Well, you might say, gee, I'm never going to be in a twin paradox debate. Well, the main thrust of this is going to be talking about a debate that's useful if you're talking to someone who has an unshakable belief system, and no matter what you say, you can't have any impact on his belief system. This will show how to make an impact on that person. Actually, I've used it. It's not only good for science debates, it's good for politics or talking about fashions or anything. So that might be good, even if you're not going to be in a twin paradox debate. So thank you very much for joining us in our 28th talk, and hope to see you for future videos.